For our basic attractive field test, we have our robot set up with the field on the other side. As we see, the robot goes at a constant rate until it reaches a certain threshold that causes it to slow down in proportion to distance from the field. We can also place the robot facing the wrong direction and it will correct itself and still reach the goal. We've also designed the goal to be dynamic, so if we move it, the robot will continually recorrect and find it again. Here's our basic test of a repulsive field. We designed the repulsive field to have a fairly small range, so the robot should just turn around and move until it's out of influence of that repulsive field once activated. Here we go. And there it goes, pointing away and moving just enough to get outside of range. And then it stops. For this test, we're testing whether the robot will reach this attractive field goal when there's a repulsive field directly in its path. Here we go. When far enough away from the goal, it'll go at a constant rate, slow enough that it recognizes with camera lag that it reaches the repulsive field. And then once it avoids this field slowly, it can turn around and swoop back to the goal. So for this test, we set up a wall of repellent fields to see if it will still go towards the goal and not be overwhelmed by those repelling fields. So let's see what happens. As you can see, the robot avoids those repelling fields and still makes it around them towards the goal. And there we go. So for our third field, we coded a perpendicular repulsive field. So this tagger will represent a vertical line going up and down the entire area and will push vectors out away from it depending on where we put the robot. Here it is in action. On this side, the robot will be driven to go in that direction. And on this side, exactly in the other direction at a constant speed. Here's a formation given by our other group. This is a goal to get to. These are both attractive fields and these are repulsive fields. Here we go. Oh. So our robot isn't performing well on this arrangement, mainly because I think the other group set their code up to have a goal in addition to the attractive fields that was stronger than the other attractive fields. We didn't do that, we just have general attractive fields, and so our robot doesn't go to any goal, it just sits there in an equilibrium between the attractive fields. However, we have found that once the robot gets to this point between the attractive fields, if we stick one of our perpendicular fields down, it'll push it in that direction further to the goal. That's a perpendicular field.
All right, so here we made a little creative twist on the attractive fields. We prioritized different attractive fields, so it'll go from one to the next one to the next one to the last one. And this demonstrates how the robot's attractive fields works and how it can turn successfully. So there's it going to the first one. Now turn, go to the second goal. And then it'll make its way on over to the third goal. Now it'll go to the fourth goal. Go, go, go. Woo!
Okay, this time we're continuing our creative idea of 4 prioritized goals in a row. See if the robot can make organized stops based on these potential fields. But we added a bunch of repulsive fields to act as hallways to guide it in a more direct manner around the path. We're thinking that this sort of method could use potential fields to guide a robot through a path in a larger maze. We just don't have room or the means to make a larger maze with the tools that we have. But as we can see, the robot can reach each goal slowly but surely and successfully navigate this mini maze.
We call this the rain dance field. So we designed this field so that the robot would rotate around a certain tile, and while it was rotating, or rather revolving around the around the tile, it would rotate on its own axis in a curlicue formation. So we call that the rain dance.
You should make this the sun.
We call that the rain dance field.
It could look like a sun or a ball.